I'm gonna start recording as soon as I turn on Zoom instead of waiting for the class to start. So maybe I'll be more likely to remember if I do it that way. So I doubt that anyone watches these things anyway, so I certainly wouldn't. All right. I think the only announcement I have is advising. We'll start next week. Registration, I guess, in 2 weeks, week and a half, or something like that. So if you haven't been contacted by your advisor, there should be a sign-up sheet on their door if there isn't one there already. One will be appearing soon because advising is supposed to start on Monday. So be sure to sign up for an advising session. I think most advisors are trying to do this via Zoom, but certainly if you have any problems or can't work things out over the Zoom link, meet with your advisor in person. With regard to, so I know this is going to come up, it's already come up a couple times, and EE471 is not being offered, so it's a required class, but you can substitute a free elective, okay, and that's any course, any 3-credit course from the university. So I think some programs have a requirement that it be a 300 level class or above, but there's no such requirement. It can be has to be a 3-credit class. So anything else? Yeah, the only elective we're offering in the department in the spring is, I think it's EE445, Industrial Electronics with Dr. Litfalian. There are a few other options. You can take several courses in mechanical engineering. Dynamics is probably the one I would recommend if you're looking for a class. Or computer science, CS215. Most of you haven't had that, so that's kind of a prerequisite for any other courses, but CS215 will also satisfy a technical elective requirement. Math classes, I think the only math classes that are being offered are linear algebra and combinatorics in the spring. So, but you may need that to actually satisfy the math science elective if you haven't already fulfilled that requirement. I looked at physics, it didn't look like they were offering any, usually they'll offer modern physics, but they're not offering that this spring. That would be another one. The only prerequisite for that is physics 2. So any questions about this class? Getting back to class. Okay, I want to talk, so we talked about pulse code modulation last time, which is a way to convert an analog message to a digital format. We still, in subsequent chapters, we'll talk about how to modulate, the digital message up into higher frequencies so we can transmit it wirelessly. But at this point, we're looking, I think, at this chapter and perhaps the next chapter, just baseband digital. signals, and in this chapter, primarily the sampling and conversion of analog to digital. So pulse code modulation is by far the most popular method for converting an analog message to a digital one. Delta modulation at one time was popular and in wide use, but it's kind of fallen out of favor and been replaced by and large with pulse code modulation. But delta modulation is a really simple technique in terms of hardware. Pulse code modulation is pretty simple conceptually. Delta modulation, really simple transmitter and receiver. It can require, and we'll see, a higher sampling rate than is required by pulse code modulation. So in this delta modulation, we approximate our analog message using a staircase approximation. We'll call M, that's a subscript Q of T for quantized. The step size is always plus or minus delta. And you must step at each sample. So, I'll try to draw, so this is our analog baseband signal, and the MQ would be, so here, we sample at this step. Let's say our current level is 0. That's typical. We start this thing off at 0. We sample, our first sample is below 0. So that means we step down by delta. A sample instant later, we sample again. Our sample value is above, so we step up. We sample again. Our sample value is higher than we are, so we step up. We step up. We step up. So each of these little increments is now our sample time. Okay. So we would continue to step up here. And then here we would step down, back up, back down, and now we'll follow it because it's going down. So that's probably enough. You get the idea. Every time you have to, you don't have the option of maintaining the same level. You have to always step up or step down. And the reason for that is it's this step up or step down sequence that's converted into our binary sequence. So, if you look at our N sample values and our corresponding step, so here we step down, and then was followed by a sequence of up steps. I don't know how many, 1, 2, 3, 4, 5, 6, 7, before we step down again. Okay, and then there we went up. We kind of oscillated going up and down there at the peak. And then it was a long sequence of down steps. So the corresponding binary message would be, when we step up, that's encoded as a 1, and we step down, it's encoded as a 0. Okay. So this is how the analog message is translated into a binary message. Now, for this to work effectively, we have to actually sample at a much greater rate than the Nyquist rate here. Okay. The other thing I wanted to indicate on this figure at least in this method, our step size is always delta, okay, some fixed value, and we'll talk about that. We'll also talk about the sample time in a little more detail. But obviously, the larger the delta is, the greater the error between your approximation and the actual waveform. You know, if you make, but you can't make delta too small, and we'll talk about why not as well. But delta modulation requires a sample rate that is much, much greater than 2W. Okay. But note that the binary rate, though, is equal to the sample rate. So that's where there could be some potential savings here. Remember, with pulse code modulation, we sampled at 2W, but every sample then would be converted to n bits, you know, 8 bits or 12 bits or 16 bits. So the binary rate was then 8 times FS, okay, 8 times our sample rate, or 16 times our sample rate. Here, you know, our bit rate is the same as the sample rate, but we have to sample it at higher than the Nyquist rate. So the question is, can there be some savings here? Can we have a smaller binary rate than what's required actually by pulse code modulation? Okay, so let's talk about how to actually generate this in hardware, and then more importantly, how do we recover our stair-step approximation? This stair-step approximation, I was going to label it as well. This is the MQ of T signal. Okay. How do we generate MQ of T at our receiver? So if we define E of NTS as the difference between this is actually the difference between the message at this point and the sample level one sample back, is how the error is actually defined. Okay, so this is called the error signal. And EQ of NTS, the quantized version, is just the sine of E NTS times delta, which this is actually just quantifying whether we're stepping up or down. And again, you can see that here. You know, it depends on, you know, if our value here is greater than the previous sample, we're going to step up. Okay, so that's what this equation is trying to get at. Then MQ of NTS is MQ of NTS minus TS plus this EQ of NTS. Okay, so let's call this equation 1 because I'll need to refer back to it. And then we can write our BN sequence as it's EQ of NTS plus delta over 2 delta. Again, this is actually just a simple formula to generate either a 0 or 1 mathematically, because EQ of NTS is either plus or minus delta. So when we add, if it's plus delta is 2 delta divided by 2 delta would give us 1, okay. But when it's minus delta plus delta gives us 0. So it's just a mathematical formula for generating our bit sequence from this quantized error sequence. Okay. So what we want to do is actually recover. So it's relatively easy to get EQ recovered from BN. okay, from our BN sequence. You know, this would be just minus delta, plus delta, plus delta, plus delta. The 0 would be a minus delta for EQ. But equation 1 is a difference equation. It's a really simple difference equation. But this is, you know, these are discrete time signals. MQ depends on the previous value of NQ plus EQ. So you can think of EQ as actually being our input. So that's actually just a first order difference. So MQ of NTS, the solution to that is actually just an integrator. EQ of ITS. And actually, we'll look at this in a little bit more detail. So draw some pictures and a sample problem in just a bit. Or substituting in for our formula for EQS, it's delta sum I equals 0 to n of 2 times 2bn minus 1. That's solving this formula for EQ and S and making that substitution directly in terms of our BN formula, or MQ of NTS is delta times 2 sum I equals 0 to n of Bn. So here, just pull the 2 out, and if we sum minus 1 from 0 to n, that's actually just n minus 1. So subtracting that. So just trying to get at a formula here where we're just doing an operation on the Bn, on what we receive. Okay. So, but this is nothing more than just an accumulator, just adding up the bit sequence as it comes in. Okay. So let's look at the block diagram for the encoder, delta modulation, encoding, or how do we generate the BN sequence? It's simpler than pulse code modulation, and that's its big advantage. So we have our sample values, NTS, and then we subtract from that the MQ NTS minus TS. That's this formula. So plus, minus, and then we compare that difference to see if it's greater than 0. This then produces our NQ, our EQ sequence. So the output of this is just, you know, plus or minus delta. If that difference is greater than 0, we output a plus delta. If it's less than 0, we output a minus delta. Okay. And then that gets fed back. There's a TS delay, so that this is actually there's actually another summer. There's another feedback loop here. This is MQ of NTS. So this is our staircase approximation. Now, that's this formula. This is actually equation 1. So both of these are added. MQ of NTS is the delayed version of MQ plus EQ. And then this is our delay to give us the MQ of NTS minus TS. Okay. And then the encoder does nothing more than, if it's a plus delta, if it's a positive voltage, whatever delta is, we output a 1. And if it's negative, so, okay. So actually pretty simple to implement in digital hardware. You know, just a couple summers, you know, a one sample delay, a comparator, and then here, again, this could be a comparator as well, the encoder, to output the 0 and 1. And so this is the encoder based on those formulas. Okay. The decoder using this formula, EQ NTS is 2 delta BN minus delta, and that's actually solving this formula. So multiply both sides by delta N and subtract delta to get the EQ. And then this is just those same formulas. This is also over there, MTS minus TS plus EQ of NTS. Okay. So this is the formula then that leads to our decoder. So we have B of N coming in, and then we decode that. But that's nothing more than, if it's 0, we need this device to output a plus or minus delta. Okay, that's our EQ sequence. Okay, and then that gets summed. We need to generate MQ of NTS. We need a feedback loop. We have to delay this. And then add that to our EQ to get our MQ. So this is the stair-step approximation. And then that actually gets run through a low-pass filter. And we get then our approximation to MT. Okay. MQ of T, as I had it drawn on the picture, is very similar to what we had with flat top PAM, if you recall. And then and we can recover then our approximation to the message with just a low pass filter. Okay, if you remember the spectrum of flat top PAM. Matter of fact, it looks identical to flat top PAM. Okay. What we need, okay, so this looks like perhaps a promising method for transmitting binary, for translating an analog message into a binary signal. What we really need is a better handle on what's the sampling rate required here. I said it's got to be a lot greater than 2W. Okay, so that's a function actually of how much error is present, which is a function of the size of our step. The larger the delta, the greater the error. Okay. There's another issue here though too. We're limited to steps of plus or minus delta in any TS interval. So if our signal is changing really rapidly, greater than that rate, we're always going to be lagging behind. Okay. So the maximum rate at which MQ of T can increase is delta over TS. Okay, that would be plus delta plus delta. That's the maximum rate of decrease would be minus delta over TS. So, but if our message changes faster than this, there's severe distortion. It's called slope overload distortion. So kind of what that would look like, again, if we have our signal changing really rapidly here, then I'm limited to deltas steps. But when my signal's changing really rapidly, I just can't keep up. Eventually I'll get there, unless the waveform is going through a series of rapid changes. There will always be this severe distortion. This is what's called slope overload. Okay. Now, even when my signal is constant, again, I don't have the option of staying at a particular level, right? I always have to increase or decrease because that's how I'm encoding the binary changes. I would need another bit state to indicate we'll keep the same level. So this difference is called granular noise. Okay. So there's two sources of error, or could be. We're going to try and avoid slope overload. Okay. We can do that by choosing a small enough sample time. Okay. Remember, if I make TS smaller or delta larger, then I'm increasing this, and I'm increasing the rate at which my delta modulator can follow the input signal. But if I increase delta, I'm also increasing the granular noise, so there's a trade-off there. So the condition for avoiding slope overload I need delta over TS to be greater than the maximum rate of change of my message. Okay. If delta TS is greater than the maximum rate at which my message can change, I'll be able to follow it. Okay. Now, the problem then becomes, how do I, quantify what's the maximum rate of change of my message? Okay. Well, at this point, we typically always fall back and say, well, what's my simplest possible message? Usually that's where something is changing. So we usually always fall back to, a simple tone, a sine wave. What's the maximum rate of change for a sine wave? Okay. Again, I could increase delta, but that increases the granular noise. So let's take a look at decreasing T of S. So I'll do that with an example. Okay. So let's say the highest frequency in M of T is a 4 kilohertz signal, and our delta modulator input is between -2 and 2, plus 2 volts. And we're going to pick a delta. Assume delta is equivalent to 4-bit PCM encoding. Find FS to prevent slope overload and compare the binary rate to 4-bit PCM sampling at the Nyquist rate. Okay. So what we're saying here is that at least the highest frequency signal in our message is a 4 kilohertz sine wave, and my system is set up so that the input's between -2 and +2. So I'm gonna feed it the largest possible sine wave for which we can for which our system can handle that input. Okay. Well, fortunately, the math here is relatively easy to find the derivative, the rate of change of my message. It would just be, I'd pull out the 2 pi, 4,000, 8,000, 16,000 pi. And then that would be cosine. Okay. But the maximum rate of change then, you know, the maximum value of cosine is 1, is 16,000 pi. Okay. So there's two things that actually go into the maximum rate of change of a sine wave. The amplitude of the sine. So, you know, here, if I have that as my reference sine, you know, and then here's the maximum slope here at the maximum rate of change actually occurs at the 0 crossings. Okay. But if I double the amplitude, that actually would make the derivative twice as large. Okay, just doubling the amplitude is going to double the max rate of change. Okay, even at the same frequency. But the other thing is, if I keep the same amplitude but have a higher frequency, you know, here double the frequency, or try to. That is also going to result in an increase in the slope. Okay. So both of those actually appear here. You know, here is the amplitude that's affecting the max rate of change, doubling whatever the frequency is. And then the frequency also appears. It's the product of those two that determine the max rate of change. The higher the amplitude of my signal, the greater the max rate of change, but also the higher the frequency, the greater the max rate of change. So that's what we have to keep up with. That's how fast our message is changing. Okay. So now let's take a look at what delta and TS are. Well, we're picking our delta so that, you know, over this 4-volt range, we're saying our delta is equivalent to a 4-bit PCM encoder, or 16 different levels. Okay. So we'll have the same granular noise, essentially, or same error as a 4-bit encoder. So this turns out to be a delta of 0.25 volts. Okay. Now an 8-bit encoder would give me a smaller delta, 16-bit even smaller. Okay. But I'm just going to compare 4 bits for 4 bits. Okay, so the condition I have is delta TS has to be greater than dm dt max, or delta, since Fs is 1 over Ts, delta Fs in this case has to be greater than 16,000 pi, or Fs has to be greater than 16,000 pi over delta, the 0.25. So stick that in my calculator, evaluate the product at pi, and I get 201 kilohertz, okay, for the sampling rate here to avoid slope overload, okay, with this message. And in this case, the binary rate would be 201 kilobits per second, right? The binary rate's equal to the sample rate. Okay. For pulse code modulation, okay, my sample rate now is just the Nyquist rate, 2 times W. In this case, 4,000 is the highest frequency. So that's 8,000 hertz or 8 kilohertz. Okay. And the binary rate then, with 4 bits per sample, is just 64 kilobits per second. 4 times 8 is 32 kilobits per second, isn't it? Okay. So unfortunately, this method requires, what is it? That's 7, 8, about 7 times the sample rate for delta modulation over pulse code modulation. Okay. Or 7 times the binary rate to have kind of equivalent performance here between the two systems, the same amount of granular noise versus step size. So, but the advantage here is much simpler generator, much simpler receiver for the delta modulation. Okay. Now, let's have you guys maybe draw some pictures and wake up here. So we want to look at another disadvantage of delta modulation, and that's what happens in the presence of a bit error in the received message. Okay. So I want you to draw what this waveform looks like. Okay. So when it's a 1, start at 0. When it's a 1, just step up half an increment. Delta's a half. When it's 0, step back down, and then step back down every time there's a 0, step up when there's a 1. So draw what that waveform looks like. Okay, I'll give you a minute to do that. So just pick out a sample time. It doesn't really matter what they are as long as they're just equal in width. Okay. And then do the same for this. Where I've introduced a bit error. It's the same message, but now I assume that, due to noise or whatever at the receiver, I've incorrectly decoded the 3rd bit. Okay. Okay, so this should look, you should get something like, you know, this here. You know, I'm going to step up, I step down one level, step down again, step up, step down, there's a step up, another step up, then a step down. Okay. So presumably, you know, our message looks something like that. Okay. The original message. But now let's take a look at what happens in the presence of a bit error. Of course, the first part's going to look just exactly like the first part over here. But now there's a mistake, and I step up instead of stepping down. Okay. And then I step up again. Okay. And then step down. And then step up. And then step up. And then step down. Okay. Now, the problem with this technique is that, you know, a bit error throws off the rest of the sequence. You know, ideally, you know, maybe after a few bits have gone by or something, I would recover and settle down in the presence of a bit error and get something that is back to the original message, looks like the original message. This technique doesn't do that. Okay, there are a couple solutions to that. Okay. Because of the accumulator that's used at the receiver, a bit error causes a permanent offset. A permanent offset. And the offset is actually 2 delta. The reason it's 2 delta is, like in that example, we stepped up when we should have been stepping down, so that produces an error of 2 delta. So after this bit error in this position, this is actually 2 delta samples higher than the message from then on. In the recovered waveform. Reason for that is the delta modulator encoder is actually a differentiator. The encoder is a differentiator. The decoder is this integrator. So we can actually recover from errors using what's known as a delta sigma modulator. And I'm not going to go into the details here, but we actually integrate the message, use an accumulator at the transmitter, okay, and then delta modulate that to get our BN sequence. Okay. This is called a delta sigma or sigma delta. You'll see either. Now, this is essentially, you know, our transmitter and receiver, but we've actually moved the integrator into the transmitter, actually. And we're encoding differences in the integration. at the receiver, we've got nothing more than actually a low pass filter from our B of N. And I'm not going to draw the waveforms here, but this change actually means that if a bit error occurs now in BN, now we're assuming we can't have bit errors here in the transmitter. Bit errors are much more likely at the receiver where we've transmitted our sequence a long distance and there's noise present. Okay. But now any bit error that takes place in BN, okay, is not going to affect, actually, it will affect at that instant, but it doesn't have an effect on the rest of the signal. Okay, so we can actually recover from it. One other thing I'll mention is what's called an adaptive delta modulator. So there have been all kinds of variations of delta modulation. Sigma delta, adaptive delta, uses a variable step size to prevent slope overload. Now, and so, again, these are all techniques that you might see in a graduate course, or you went to work for a company that worked in communications. You know, you do additional research into these more advanced delta modulators to see what they do. But the idea here, it's actually pretty simple. If you've got a steep change, so we first step up by delta, okay, but after the first delta, 2 consecutive up steps, the second delta would actually be 2 delta. And the third would be 3 delta. Because the assumption here is if we got 3 consecutive steps in a row, we're trying to catch up. Okay. And this is actually easy to, I mean, it would still be encoded as 1, 1, 1. Okay. But now at the receiver, we know adaptive delta is being used, so we know it's not delta, delta, delta. At the receiver, we would generate a delta step. We've got another one, then followed by a 2 delta, followed by a 3 delta. Okay. And then, you know, here we still haven't caught up, so it'd be a 4 delta step, okay, which really overshoots. But the next one, we know we have to step down. And here the techniques will differ. It might step down by 4 delta. It might just step down by delta, and then by 2 delta until we catch up. Okay. Usually at some point, you know, we get back down to delta and we're just oscillating around. Okay. But these are much more, as you can imagine, finding the error due to granular noise here, it's much more difficult to analyze. You wouldn't do this analytically. You'd do this actually with computer simulation, you know, using MATLAB or something, and then actually generate the waveforms and calculate the error using MATLAB. But this is just one variant on delta modulation. But in the homework, I think I just gave you problems related to calculating the sample time to prevent slope overload for delta modulation. Okay. That's it. Have a good weekend.